introduction. Hello, everybody. And today I will talk a bit about optical nonlinearities in the gigahertz to terahertz ranges. And I have fully theoretical work, and I have two collaborators on theory, Apostolakis and Julia Shevchenko in Prague. And at the moment, two experimental collaborators, Vladimir Vaks and Nonlinear in Nizhny Novgorod. So they are working on terahertz and gigahertz experiments, and we compare and contrast with our theory. Okay, so first of all, I would like to give you an idea why we are doing these things in terms of applications. I will give you a very short outline of how we developed the theory and show some simulations. And then I'll close it with the control of gigahertz and terahertz nonlinearities. We managed to control them by several orders of magnitude. So I'm involved with a few projects at the moment, and from the mostly terahertz mid-infrared, mostly mid-infrared actually, we're looking into controlling the quality of water in different parts of Europe. We have we use developing QCL and photoacoustic detector sensor. And our role is to help with the theory for the company that develops it. This is integrated in a big project called Alco3S. I'm, of course, interested in the nonlinear optics itself and on the development of new methods and computer software applied to quantum transport and optics. So we have a few books that summarize a number of results and applications of gigahertz, terahertz, and infrared radiations. They are all published by the NATO Science Facilities for Peace series with Springer. And these are our current books. We're hoping to have a next one in a couple of years. So our project, so as I mentioned, Alco3S controls the quality of water using different types of detection. And now we'll start Odysseus, which will look into explosive precursors, also using a number of detectors, including our far infrared detectors and sources. But going back to what I'm really going to describe more today. If you have optical transitions, they can be between conduction and valence subbands, like in a conventional semiconductor laser, or they may be between subbands, like in a quantum cascade laser. So these have the advantages of having the chance to go to very small energies, which are not possible in materials with a fixed band gap, and allows us to reach the terahertz range. So what I'm going to show here today is something that is not based on optical transitions, but rather on electrons oscillating due to Bloch oscillations in the semiconductor, and that allows us to go to even lower frequencies from gigahertz to terahertz. We will be looking into superlattices like gallium arsenide, aluminum gallium arsenide, and here you see a picture of the actual structures, such as we are going to investigate in this talk. Okay, so the method that I use is a combination of non-equilibrium Green's functions with solutions of the Boltzmann equation. And non-equilibrium Green's functions are very useful because you have a whole series of corrections that you can add to make the problem as precise as possible, including the interaction in higher and higher orders. So you see here our propagator of full Green's functions, and here is the self-energy that takes into account the different scattering mechanisms. So for Hamiltonian, I have the kinetic energy, of course, the superlattice potential. I have a mean field, which appears when you polarize a superlattice and charges are left behind. We have the applied field itself, and then we have many particle corrections. So this, 'this is a numerical problem, and if we reach convergency, we can then look into physical quantities such as population densities, currents, and optical spectrum. Okay, so I have a few scattering mechanisms in our problem. I include electron-atom scattering. You see the self-energy here. I include impurity scattering. I include something which is very important for this problem here, which is interface roughness scattering. You see the Hamiltonian here. And allow-Froment scattering. So these are the main mechanisms included in our solution of the Dyson equations. And these can be used both for our superlattices and for quantum cascade lasers. You see here a few of the simulators that I took part in co-developing over the years. You see here, it's very interesting, this case of transmission. You see there are hundreds of transitions involved in here, and the theory can actually predict the evolution of the spectrum very well. This is a mid-infrared case, this is a terahertz case. And how do I actually solve my problem for the superlattice? The problem is the following. The current non-equilibrium Green's functions code that we have has convergence problems for very small frequencies and high powers. So what I do is to combine input from the NHF code with solutions of the Boltzmann equation in the relaxation rate approximation, for which I have analytical approximations and for which I can put whatever power I want and still works. So basically, I have a static and an oscillating field at a given frequency, and due to the nonlinear behavior of the current voltage, harmonics are generated, and these are the expressions that are programmed in our method. If we have perfectly symmetric current voltage, if we have the same kind of scattering mechanisms for positive and negative voltage applied to the system, we have a completely antisymmetric voltage curve, current voltage, which is similar to what Isaac and Sue predicted many years ago. The difference is that we can calculate it. So we know what are these points here, for example, we know what is the peak of current, and we know what is the characteristic voltage or energy of the system that characterizes the negative differential resistance range, which is here. So this is completely nonlinear. It's completely different from your resistor in an electronic circuit in which voltage is constant resistance time current. So if I put a given frequency here, multiple frequencies are generated. So my colleagues can measure this, okay? And interestingly, what happens is that the interfaces, for example, of gallium arsenide and aluminum arsenide, they are not the same. Aluminum arsenide sits well over gallium arsenide, but gallium arsenide doesn't sit so well over aluminum arsenide. So if the current goes this way from here, from bottom to top, or from top to bottom, the scattering is different, and the voltage current is not completely antisymmetric anymore. So everybody's expected that superlattices could only generate odd harmonics because of a completely antisymmetric curve, but actually even harmonics are also measured. And you see here in this curve, you see measured current and experiments. And I don't really have an exact solution for the case of asymmetric current voltage when this peak is not equal to this. So I use an ansatz, which I assume that, the current here, the top current here is different from here, and the current top, the turning voltage here is different from there. So this ansatz solution allows me to modify the analytical solution and get working relations for the power output based on this nonlinear current that we see here. So these are experiments. So these symbols are experimental harmonics. So we see a third, fourth, fifth, sixth, seventh harmonic, and the line connecting are the results from the theory connecting these points. So see, it's very good. And we can predict the even harmonics, which was unexpected in the past. So we explain it through the fact that the current is not completely antisymmetric. And when you put given frequency, you can get even and odd harmonics. So basically the electrons are oscillating, and what we have is a modulated log oscillation. Okay, this is what the underlying physical mechanism for this emission. Unfortunately, you have to put a superlattice in a specific waveguide, so you can inject, for example, GHz radiation, inject it with excite antenna, and the oscillating gigahertz current goes through the superlattice and harmonics are emitted. When you do this, a lot of power gets lost. And if you use a tunable source like a BWO, if you have, for example, in our experiments, we have seen that in the experiments before with my colleagues, for 1.8 milliwatts hitting the flange of the waveguide where the superlattice is, my calculations are consistent with only 61.6 microwatts going through. And we can explain the whole theory with this number. So we could actually use this theory to see how much power actually gets to the superlattice. Of course, we're trying to get better solutions for the waveguide and superlattice system to have more power. But the important thing is this is so nonlinear, so completely different to usual nonlinear optics that just putting more power doesn't help you. So what I'm showing here is like the efficiency of a generation, third, second, and fourth harmonic by changing this asymmetry level here, by making the current less antisymmetric. So the more antisymmetric, the higher the odd harmonics. When I lose this, I increase the even harmonics, as you see here, and the other harmonics go down. So this is a phenomenological design by just changing these ratios between the peak currents here and there. Okay, and the peak currents and the turning voltages there are connected in our theory, so we just have to change one, and everything else is connected. If we look at available powers for the sources that we've been using, like GaN devices, sleds, PWOs, we see that for the powers and frequency that they can currently generate, we expect this range of power output. Okay, we expect at the moment micro and nanowatts coming out from the different harmonics. And interestingly, we can also describe this with a more precise theory in which I don't really use that analytical ansatz, but then I have to solve path integral numerically. So I have a rank-root solution for the momentum and the velocity for the electrons going this way or that way. I fix the scattering times by saying that they are different. The scattering times are the same as the turning points for positive and negative energies. I put this in the theory and I can have clean numerical solutions without any numerical error. The problem with my ansatz is that it's not differentiable at the origin, so I have some numerical mistakes that build up for low power. So this is how we control, for example, the emission for a few harmonics by playing with this asymmetry in the voltage. You see that as for even harmonics, there is a very well-defined region in power and asymmetry region that maximizes my output. And of course, you have, if you have no asymmetry, you don't have any emission. And you see here that increasing the asymmetry will reduce the odd harmonics, and the higher the harmonic, the more power you have to get in. But more interestingly is that just increasing the power doesn't help you. See, there's a maximum here for all cases. And this maximum is due to a judicious combination of the different mechanisms. So this is completely different from usual nonlinear optics like Chi2, Chi3, Chi4, Chi5. When you put more power, you get more output. This doesn't help you here. You see, I have here more input power. Alpha is related to the electric field amplitude. So I have more power, more input power here, and I have less output than in here. So it's completely nonlinear in a completely different way than the usual nonlinear optics, which makes it very interesting for theory and experimental physics. So here are some predictions for higher harmonics. Okay, this is the third harmonic, fourth harmonic, fifth harmonic, sixth harmonic, and you see those petals that develop if you have very high voltage. So far, we could not go to such high voltages without destroying the samples. So we have been working only in this region here. And we have used for a fixed voltage current, which had some asymmetry, we applied the voltage and we managed to increase the emission of the internal harmonics by several orders of magnitude. So you see here, this is the measured IV, and the solid curve is the result of the theory. In this case here, we can note that you can also, if you can't do non-equilibrium with these functions calculations, you can take the IV measured and pick these points by fitting my ansatz formula and put this in the theory. So we have here two beta lows, one for detection and one for emission. For detection, we use a similar wave mixing and we use heterodyne detection. You see here, so we have the superlattice being used in both source and detector for these frequencies. And the superlattices are housed in waveguides like this. So what we get, this is very nice. You see here, fourth harmonic and sixth harmonic. This is the experiment, and this is the experiment, and this is the theory. So you see our prediction showing a high power here, super consistent. What is predicted, what's measured. This is experimental error here, so noise. Okay. This is also noise. And you see everything that we expect, that the higher harmonic, you have to put more power, but just putting more power doesn't help you. You see this is very well defined here, a maximum output that we can predict. And this helps us to guide our experimental colleagues when they want to do spectroscopy with superlattices. That helps us to them to tell which power they should use, which voltage to apply for each harmonic to maximize the operation to several harmonics. So we start with 100 gigahertz, and you can go all the way to terahertz with reasonable power, enough to do spectroscopy. I'm not going to talk about the current experiments which are being performed for metabolomics, but these superlattices are currently being used to detect metabolites in the urine after chemotherapy that cannot be detected any other way. So we use this control of the nonlinearities to control the output and exploit several harmonics. So this then, we have seen that we can control the nonlinearities with voltage, we can control with intrinsic asymmetries in the IV due to the different scattering mechanisms. What happens if you combine both? Basically, if I put the voltage and I chain, and somehow I have an interface or a given design that gives me larger symmetry. And it's very interesting. First of all, if you look at this combination, you see that some devices should operate very differently for their characteristic frequencies. For example, for the frequencies we have currently on BWOs, you see that the voltage doesn't help you too much because we are in regions here. And the most interesting, if you look at this picture here, this is the power output with both voltage and increasing breaking of symmetry, means that we can have higher power in even harmonics with less voltage applied. So it's a good combination because we know that we can't apply too much voltage without breaking the sample. So these studies continue, both further developing the theory, looking for better solutions, and looking for other nonlinear effects in this range, and it helps us to guide our experimental colleagues on how to select each power and voltage to look into different harmonics, to look into specific resonances for many biological molecules that we want to detect, both in the case of checking pollution in the water, looking at blood samples, urine samples, and also breath analysis. And we can choose gigahertz frequencies in which water doesn't affect the absorption too much. It's very good. So in summary, we have the chance to develop quantum transport and optics with interesting cases, going further and further in non-equilibrium Green's functions and more clever solutions of the Boltzmann equations. At the same time, we can control the nonlinearities in this range by orders of magnitude. And we have a number of applications, and we are helping our colleagues to design new devices. So we are looking into different superlattice structures which maximize some harmonics to allow us to look to very specific molecules that are of interest to us. So if Khalifa University is not very well known, it's very new, but we already jumped to classification 183 in the QS classification, and we're going up, up, and up. We're hiring very good people, we have excellent conditions, and we have a number of fellowships for PhD students, and we also have some possibilities for postdocs, and we are looking for faculty for the physics department. So our applications are to nonlinear optics, protecting critical infrastructures, mostly water structures, detecting explosives, using it for breath analysis, for metabolomics, in which we use, we can detect metabolites that generated through chemotherapy, which don't appear in, cannot be seen in any way if you are doing conventional clinical analysis. So that helps us, helps my colleagues who work with doctors to find needful corrections to the treatment as they do the chemotherapy and find problems notably to the liver. So thank you very much. That was it. And if you have any questions, I can try to answer them.